In this video, we're going to look at a whole bunch of things to do with titration of a strong acid with a strong base. In fact, here's what we're going to tackle. Firstly, we're going to use the titration technique to determine the concentration of one of the unknown concentrations or volumes of the acid or base. Then, once we figure that out, we're going to do a few calculations. We're going to figure out the pH of the acid. Then we're going to get the pH a little bit of the ways into the titration. We'll call it before the equivalence point. Then we're going to get the pH at the equivalence point. Then we're going to get the pH slightly past it. And then we're going to get the pH of the initial base. And lastly, we're going to make a little graph of all this stuff. So the way I've set these questions up is that our pH will increase towards 14 as we go through 2 through 7. So here is the question. We're going to place 30 mils of 0.2 molar HCl, which is a strong acid. Look it up if you're not sure. You're going to put it in a flask. We're going to determine the volume of 0.1 molar NaOH that is required to neutralize this acid. So I've got an equation written out here. You'll notice everything is a one-to-one entity. So let's proceed. First step of this question is we find the moles of the HCl because it's already in the flask, and we know the volume and we know the concentration that I underlined above. You take those two values and you multiply them together, and you get 6 millimoles. We're going to be working in millimoles here. That'll make our lives a little easier. So 0.2 times 30 mils, 6 millimoles. Next step is we're going to find the moles of the NaOH. Now, this one's easy because our mole ratio, which is going to come from the equation up here, it's got to pretend 1 in front. So we're going to write 1 mole of HCl. And then the other substance here also has a little pretend 1 in front of it. So we're going to transfer that 1 right there. Now, not every question it is 1-to-1, but this one is, so we're going to cancel, and we still have 6 millimoles, but now it's of NaOH. Moving on to our last step, the volume of NaOH. This is our equation for volume. We know the millimoles are 6, and the concentration is given up here in the question as 0.1. That will allow us to divide and figure that we need 60 mils of this NaOH solution to neutralize the 30 mils of 0.2 molar HCl that's already in our flask. Now, once we've done that, we can proceed with this question. So first thing we're going to do is the pH of the acid. And this is going to be really easy because HCl is a strong acid and we already know its concentration is 0.2. We can simply just take the negative log of 0.2 and we get an answer of 0.7. Now we have to ask ourselves, does this number fall in the acid range and in the pH scale? Acid range is 0 to 7. So the answer would be yes, it does fall in that range. So we can keep that answer. Number 3, calculate the pH before the equivalence point. So here's what we're going to in fact do. So we're going to calculate the pH of the solution after 20 mils of NaOH. That should be really just 0.1 molar NaOH. Has been added. Now remember, it took 60 to neutralize it, so we're adding in 20, which means once we've added this 20 in, our solution is still acidic. We need to remember that. So once again, we've got our balanced equation here, and what I like to do is I like to figure out how many millimoles of each substance, the acid and the base, we've actually got going on in this question here. So we actually already did this one for the HCl earlier. I can remind you that we have 6 millimoles of the HCl. Now, in this 20 mils of 0.1 molar, we've got exactly 2 millimoles of this base. So what's going on here is what's the number of unreacted millimoles of the HCl? Well, we're just going to subtract the 2, and we're going to get 4 millimoles. So there are 4 millimoles of HCl that has been unreacted. Again, it was these two numbers we subtracted. So the 4 is the difference in the 2. Now that we have that, we can figure out the new concentration of the solution. Why is it a new concentration? Well, because we have fewer millimoles of the HCl, and we've actually increased the volume. The volume of the solution in the beaker right now, or the flask, is actually 50 mils. So we can take our 4 millimoles and divide by 50 milliliters. And when you do that, you get 0.04. I would think that would make some sense. Remember, our initial acid started as 0.2. We've neutralized it. The value has dropped. And so all we can do now is just take our values, plug it in, and get 1.4. And again, ask ourselves, does this number fall in the acidic range? And yes, it does. So 1.4 is our next answer. Moving on here, we're going to calculate the pH at equivalence. And this is going to be really easy because they are both strong substances, strong acid, strong base. That means that our equivalence point where the moles are equal, it is going to be at 7 every time. There's a I don't know why I put the balanced equation up there. But if you think about it here, we've got, this amount plus this amount. It's all been neutralized. All we really have left is water. And what's the pH of water? The pH of water is 7. And then we have NaCl in there. We've got salt water. And neither the Na or the Cl affect the solution in any way. So there's proof that our pH is at 7. You just got to memorize that. Shouldn't be that hard. Okay, now we're going on to when we've just gone slightly past the equivalence point. So let's calculate it after we've added in 65 mils of base. Now the point, I debated whether or not how to phrase this question. Initially I said we're going to calculate the pH after there's been 5 extra mils of NaOH added in. Then I decided just to go with the total volume. So remember we added 60 to neutralize the 30, but in this now I'm saying we've added 65 in total. So again, we're going to have to figure out the millimoles. We don't need to worry about the HCl because it's all been neutralized. In fact, all we need to worry about is that extra 5 mils of base that has been added in. We're 5 mils past the equivalence point here. So all we're going to do is we're going to take our volume, which is 5, and our concentration, which is 0.1, and multiply them together. And this will tell us how many millimoles of base are in our flask currently. Once we've done that, we need to recalculate our concentration because the total volume of solution in our beaker is now 95. So therefore, let's take our new number of millimoles and divide by the total volume. That gives us that value. We're going to negative log that value and get an answer of 2.28. Now, does this fall? It should say in the basic range here because this solution's basic. It shouldn't say acid here. It should say basic. So does 2.2 fall in the base range? No, it doesn't, which means there's an extra step. We just need to take 14 and subtract 2.28. In fact, we didn't figure out the pH here. We actually figured out the pOH, but whatever. We'll just subtract, and we get 11.72, and that is the concentrate. That's the pH of our basic solution. Remember, it's now basic. We have more base in there than we do acid. So last question here, we're going to calculate the pH of the base. We could have done this right away. Let's not forget here that we have this number right off the bat. Sometimes you don't have that in a titration, so we'll just do the negative log of 0.1, which is 1. And again, this is a base, so we're just going to go 14 minus 1 to give us an answer of 13. We can make a graph now because we have a bunch of pieces of data. I think the first thing we did was we figured out the pH. We've got volume of NaOH on the bottom, and we've got pH going up here. And the first thing we did was we figured out the pH of the acid solution on its own, and it was about 0.7 if I'm remembering. Then we added in 20 mils of the base here. We added in 20 mils, and the pH went up to, I think it was 1.7. Then we went to, I believe it was the equivalence point here. Now remember, the equivalence is at 7, so I tried to go for 7 on my graph. And remember, we had added in 60 mils of the base at that point. The next one we did was we had 65 mils of the base added in, and that brought our pH all the way up to 11.2. And then the last thing we did was we figured out what was the pH of the base in itself, and the highest it could ever go was about 13. So our graph will never actually reach 13. It should always be just a little bit less because it's been diluted. Now you can connect these up, which is a good idea. And what's really going to happen is our pH is going to stay fairly constant until we get very close to the equivalence point, and then we're going to see a drastic increase. So it probably will look a little something like this. It's going up, it's going up, it's going up, it's going up slowly, and then all of a sudden I missed it, and there's quite an increase here, and then this should go on like that forever. It doesn't quite touch it. And that's what your pH graph should look like.